Okay, hello again to everyone. Well, this is the last presentation for today. It will be really short because it's just to show you a few examples. Even I put here, well, properties of thermal barrier coatings, but I think it's enough when I told you for the insulation, and I just want to show a few examples. Okay, just the classical introduction about the days, just to, well, like this one is the last one. Tomorrow we'll talk about the ceramic matrix composites, okay? More in detail, first a classification, okay, and how they can be processed. Then the second one will be about, well, ceramic composites but containing carbon nanotubes mainly, and the third one will be about silicon carbide, okay? But well, today it's about the properties, and well, I just want to show you a few examples, and well, maybe properties like that one is how it modifies about the time, because well, here is about the spray and how it works, how the stencil or the erosivity of the coating works. But something that at least I want that you have in mind is that the thermal barrier coatings is for protect, but it's not like, okay, I want to coat or protect for 10 hours or 20 hours. The idea is to work like several hours, okay? You cannot do all the time like a coating to protect your metal substrates, okay? It has been there for a really long time and many thermal cycles, okay? Well, and as I told you, here there are a few examples, not only about the thermal barrier coatings, if not how we can use these guns for repair, for example, that is also quite important, the materials. And here is a couple of examples, unfortunately again in German, about the plasma powder, about different materials. And for example, this is for the extruders, how are erode through the friction with your metal or your ceramic particles, and then you need to repair it, okay? Here more examples about this paper milling, okay? This is the really big cylinders that are rotating, and well, how we need first to remove it and for the reparation, okay? And here more examples. As I told you, this one will be more about examples, but real examples, not in a lab scale, like really in companies, these really big rolls that you need to first to grinding and then to coating. And again, and well, you ask me about the roughness. Probably, for example, in this kind of application, the roughness should be really low, but for others should be really high, because this one is for a rolling, and of course you want to reduce the friction, okay? Here more example. Of course, we talk all the time in the others two about the gas turbines. One gas turbine with all these small vanes that you can release. Here one of them, but there are applications for others. Well, I was talking with you a few minutes ago with some of you, and many people is interested in this in general of the batteries, but always these several coatings or different parts can be done for the processing that I showed you yesterday, or also by spray techniques. Also in the hydro power generation, here there are always a lot of friction and several coatings has to be done. I think I have a couple of pictures about the wear in some hydropower generation and how the coating works, okay? Also, well, here insulated bearings, they should be coated. For example, for wind power generation, in that case, it's to reduce the friction. Also here, for example, in the Shinkansen in Japan, the really high velocity train. I don't know if you have the opportunity to go in one of them, but it's amazing. It's really fast, and yeah, it's always like possible by this kind of coatings and low friction, okay? Other examples, for example, here in the steel automobile, different furnace that here you see how it's the coating, or here, for example, other coatings. Also in the cars, of course, several parts are coatings. These galvanizing lines in different components of the engine. I don't know exactly which one, but always that are high temperature it should be coated, or the other hand, if you have a really large friction, also the coatings should be there. Okay. Again, examples in the paper mill. Yeah. For example, well, the picture maybe is not the best one, but how it's coating, then they grown to have a really low friction, and well, how all these processes are done in order to avoid the sticking of coating. For example, for that reason I told you that probably the low friction, because we are talking about paper mill, it's moving all the time. Of course, the idea is that there is not a sticking between the contact between your coating and the paper. Okay. Other examples, this one how it's cut, but really for this one is a furnace to work at temperatures higher like 1000. And also, well, thermal barrier coatings are mainly, thermal barrier coatings are only for high temperature, but also it's important that these coatings work in other properties like the wear resistance, these tribological properties that we talk. And well, here is not only high temperature materials, as I want to show you some examples. Here, this technique we talk a bit in the previous presentation, but also it works at room temperature. For example, yeah, also for a lot of things for food or different blades, or well, this case are for high temperature, but could be not. It's only the importance of the wear, and also which kind of wear it is. Okay. And here is one example about these solar turbines companies. Okay. Here another examples. Yeah, we see this one is even with polymers, that the people working in polymers for a Rolls-Royce turbine. Some components that should be coated, and again that I want to show you is that you see, I mean, these techniques are really used in really big components for really important companies with this combination, okay, of aluminum and polyester, that is this dark phase, that means dunkel, here, and can be injected like that, okay, with different gas, and you produce it. In that case is like the bond code nickel and chromium aluminum compounds. Other examples, yeah. Here, for example, in order to reparate the turbines, also first the milling and after the coating, and this is how they looks like. Okay. More example now about the plasma with the alumina, how it is coated. This is a picture from Volvo. Okay, also important company. Well, in that case for turbine, but also for the automotive. And here, well, one example of the cross section. Here, in that case, they need low porosity, and well, the bond coat, that is this white part that you see is not really homogeneous, but at least is the continuous one. And well, as I told you, some examples about the thermal spray coating for water turbines is not only for high temperatures, also for other properties. In that case, that use this this material, the wolframium carbide. It's really, they present a really good tribological properties, and in that case, well, it's a mixture, and they coat in these plates with these characteristics. For example, again here the roughness that are required, because always it's quite important. And well, more and more examples. In that case, about Rolls-Royce for the guide vanes. This is for the hot flux air that it can moves, and then you need here. In that case, this is for high temperature that is told here, because the idea in that case is to go above these 1300 degrees. But using instead the yttrium stabilized zirconia, this porous magnesium spinel. More examples here, as you see. Well, this is 100 microns. The coating is so thick that also we discussed about that. More examples, not only high temperature, also hydro erosion. Of course, there is a lot of friction in this part of the metals, and if it's without any coating, the material finally, after several hours, or like that. This is from for a company. And then, well, here the idea is to coat the material to avoid this erosion in the blades. Okay, and well, this is how they look like. This one with the coating after trimming with these metal compounds. Okay, they look like quite well. If they don't have any coating, this is the uncoated material, and obviously this is after the use you see that there are a lot of friction and a lot of erosion. Okay. Also examples, a lot of people talk about the solid oxide fuel cell or ask me different things. Okay, this one is the classical scheme. Of course, you have your electrodes, your cathode, your anode, the electrolyte to move the oxygen, your gases and your oxygen, of course, like it works as solid oxide fuel cell, but you always need to protect the contacts between the collectors and different components, okay, in a really complex structure. And here, for example, is one of the examples with the current collectors and reaction zones that you should avoid, and for that, well, the people is working in this kind of protection layer, okay. In that case, a combination of high temperature, but also about reactivity. Yeah. But they are produced, well, in that case, by this atmospheric plasma spray, but also by the slurry base barrier. Also, yesterday, I don't know if you remember, I told you different possibilities to create coatings, but well, this one is also another possibility. Okay. Mortarger, for example, this one for solar cells. I would like to do more or less overview how they can work. Okay, this is also, I mean, the commercial ones. In that case, with the classical indium oxide that is for this ito material, also the thin oxide that is quite, or is maybe the future in the solar cells and these kind of materials, because this is a good part. Practically all of them can be coated. Here just one example, like the before in the previous one, it's about the problem when we work about the several number of cycles. Like here you see, well, it's 500 hours, several numbers of failure, how this TGO grows and induce the failure, just to have in mind again. Here, but of course I don't want to go in detail, I just want to show you a few examples. The modeling, how it works about the different thermal cycle and the vertical stress, the compression stress, the tensile stress in all of them, because this is totally critical. And well, to estimate the time, that is obviously is critical, and is for that was the idea of the title of this presentation about the properties. But all these properties should be controlled, or then check what is the number of cycles that you can work. Also, well, the 3-point bending or dilatometry of your compounds, because of course with the expansion and the sintering that happens when you increase the temperature of your thermal barrier coating, in that case, of course, this sintering that this happen, that is not desired, but it happens, reduce your lifetime, and also the properties of the TBCs. It should be calculated, and you should take into account that if you want to go further this temperature using the heat stabilized zirconia. If you want to go further, it's better to use other materials. Everything that should be controlled. I mean, this field is really wide. Yeah. Also, other thing that you should have taken into account is the phase transformation during the high temperature. Depends, for example, in the content, the yttria that you put to stabilize, it will affect the final properties of your material. If you produce the cubic phase or the tetragonal phase or all the possibilities phase, because of course it will affect your material. Here, well, more examples, and this case about the properties, but more talking about the failures. When the temperature is so high on the surface for the heat stabilized zirconium, for that is required other process. It can produce the spallation. The limit is like that. This is just a little bit more than 400 cycles, but it should be taken into account, and for that it's important to normalize the test and depend on the techniques that you use, and if it's good for the cycle oxidation, or it's better for the corrosion, or for the erosion or temperature. I mean, you should think about that. It's really wide, and depend your final application, you need to think what is really the coating that you want and for what. Okay. For example, this is a perfect example. This is more expensive process, this vapor deposition, but for that case it is totally required. Okay. For that conditions, we see this a really large increment with the year and the research. Of course, with the optimization of that one, the number of cycles at a high temperature increase. It's not only that, okay, I will create a thermal barrier coating or a coating for wear and do it, and that's all. Of course, it requires several years or several times working on that, and well, the properties can be modified, but depend on your properties that you need. Okay, and here, well, I think I'm more or less relatively close to finish. Is about this process, this problem that I told you about the volcanic ash, for example, from this CMAS, that is the reduction of these calcium, magnesium, aluminum silicates that are always attacked, and it's a really big problem for the thermal barrier coatings. Okay, then we focus on that part with a Barnett ring testing over samples with different conditions, with a really high temperature for the thermal barrier coatings, using different, for example, in that case, 400 microns of the yttria stabilized zirconia and just 150 of the bone coat with different conditions, as you see here, because the idea is exactly to do that. You have here your TBC and here your volcanic ash, that at the beginning they are melt, they impact in your coating, and when they are liquid, they start to penetrate, as you see here. Okay, they start to penetrate in your bow coating. If it's still high temperature, obviously it's a problem, but the real problem is when they cool down, that then they incorporate in your material, but also produce several cracks through the expansion. Okay, then there are a different possibility to avoid that, to present a resistance against the presentation. Well, here is the name of the famous volcano. Well, now I can talk German, but I cannot talk Iceland. This is the next level. And well, here one case of these silicates, how they penetrate. Okay, and for example, for these pillars that we create, and with the TMAS, we see, for example, again for this silicon, that the penetration is quite high, and then achieve your material, and then this is obviously a really big problem. And now the idea is focusing how to stop the silicon here. There are a lot of investment there. If you have ideas, you are totally welcome to share with us. Okay, and this is, for example, how they look like at the end. Okay, about, well, different because, well, obviously this is one of the problems. I don't know if I have here. No. Okay, the problem of this volcanic ash or ash in general is that it's not always the same. I mean, maybe the content in one part of the world of the calcium is higher, in other is the aluminates is higher. I mean, it changes, and then it's critical for your barrier. Okay, just to mention, if you are interested, for example, this researcher Nichin Pachur, he works several
Sí, es que no escucho nada.
Sí, sí, sí. ¿Me oyes mejor? Vale. Yeah. Vale. Well, and here just a few examples of the penetration of these elements that are really critical. For example, here the calcium, obviously they start to penetrate through the cracks. Here by EDX, you know what is EDX techniques? Well, that you can do with EDX, it's basically that you can choose, for example, in CM pictures, well, through a different reason, of course, of the electrons, you can produce like that, like mapping of different elements. And for example, in that case, it's quite useful to see the penetration. For example, also here, this kind of bubble from the CMAS and how they penetrate. Here is clearly the silicon and the alumina, some silicates that penetrate. Or here some calcium, probably silicates. Yeah. And again, more penetration that obviously should be avoided, and for that, like it's up to now, there is no possibility to stop this penetration. The only solution in that moment, and if it happens again, is to stop, for example, the flight. I mean, there is no solution until now. Maybe in the future it is, okay? And well, this is how they fail by these CMAS, of course, because they reduce the stiffness. Is that I told you. The problem, of course, is the infiltration, but the real problem is when they solidify during the cooling, because then they are really stiff, your coating, and then it will be break. The strategy is up to now. Well, once is, of course, with a tensor microstructure, then it cannot penetrate, but it's not enough. And then other alternative, it's use materials that can crystallize these elements, or then incorporate in your structure, and then if you incorporate it, they cannot continue penetrate. Okay. But the problem is that it's a really high temperature for several hours, and maybe you can stop or hinder, but at the end it will be there. And then up to now there are not a clear solution or strategy. Yeah? And that's all. Again, thanks for Professor Robert Fassen to be always there for all the questions, and well, in this case you for listening me during this morning. Yeah. Thanks. And questions again, if you want. Well, you can ask me whatever you want, but yeah, it's lunchtime, and I think so it's better. Then thank you, and see you again tomorrow.